Welcome to lecture 5 for the course AI 61003 Linear Algebra for AI and ML. In the last class we discussed about the concept of norm and distances, and mostly we restricted ourselves to two norm or spectral norm and the Euclidean distance. So what we want to do today is we want to continue that discussion on norms and distances further, and today we want to talk of one of the most important concepts once again in this area, that of standard deviation. Okay, and this standard deviation, how is it standard deviation, and how is this standard deviation related to the concept of norm. Standard deviation of a vector and how is it related to the concept of norm. So this generally is not covered in usual linear algebra course. This is very specific to this particular course because in data science or in AI ML applications, if you have some hands-on experience previously, then you would realize that many a times you sort of decentralize the vector. So you sort of demean it, you subtract the mean from the vector, you divide it by the standard deviation and make it sort of mean 0 variance 1 vector in order to subsequently put it through further analysis. So what is it that we are really doing here, and what are the linear algebra operations involved in this particular process is what we are really going to see today. Standard deviation of a vector and its relation with norm inner product. And another important concept that we want to do today is angle between the vectors. And this concept of angle between the vectors is going to be used to define one more different type of similarity, which is different than the similarity that we were talking yesterday, which was based on distance between the two vectors, distance coming out because of the Euclidean norm. So that's the agenda for this particular lecture. So let x be a vector in Rn, let x be a vector in Rn. Then please remember, by this notation average of x, what we really mean is that we have this 1 transpose divided by n into x. That's what we have. So this is nothing but x1 plus x2 plus xn divided by n. So that's the real number. Average is a real number. So given a vector x, you can find out this average, and I can define a new vector. I can define a new vector. X hat is defined as x minus this average x into 1. So this 1 is basically 1n. I will write, I may not write, it doesn't matter. So what I am doing is that this subtraction is a subtraction of vectors, and what I am really doing is that I am subtracting every entry of vector x by its average. So that's this operation is really doing. And then what I can do is I can look at the RMS value of x hat. So that RMS value of x hat is nothing but the standard deviation of x. So standard deviation of x is nothing but RMS value of x hat. So so how do I define standard deviation of x then? The definition of standard deviation of x is RMS of x hat. And what is RMS value of x hat? In yesterday's class we had defined RMS value. So how do we define RMS value? So this is the definition of RMS value: x1 square plus x2 square plus xn square divided by n, or 2 norm of x divided by square root of n. So that's what we will do. So we are looking at RMS of x hat. So RMS of x hat is first component xi minus average x, and that is the ith component. So you will have sum of squares I going from 1 to n. That's the norm square of x hat. You have to divide it by n. So this is mean square of x hat and in order to obtain root mean square, you will take a square root of it. So this is the root mean square of x hat, which is nothing but the standard deviation of x. So if you really want to convert it, then you can see the standard deviation of x. I can write it in this particular format: the vector x minus 1 hat 1 transpose x divided by n into 1. It's 2 norm divided by square root of n. That's what I am looking at. So it's no big deal. I am just substituting few terms here. So for example, I am looking at this entity is basically the 2 norm of x hat, and this x hat I am writing in this particular fashion. So average x I can write down as 1 transpose x divided by n into 1. So that's all I have done. So this average x is being substituted by this particular formula, and that's what I have written here for x hat. And x hat, it's 2 norm divided by root n, that's the RMS value of x hat, which is nothing but the standard deviation. So what is basically standard deviation? So standard deviation is you look at the d-meaned vector, and its RMS value. So what is the interpretation of standard deviation? So interpretation of standard deviation basically is the measure of how far you are going away from the mean. So typically how far you are away from your mean value, that is what the standard deviation is measuring. So this is something that is quite useful tool to have. So the typical value of the vector entries is the average, and you are wanting to measure how far you are from the typical value, that's the average of x, how far. That metric is given by standard deviation. That's something that is very useful. The important note here is that the formula of standard deviation of x involves square root of n here, but you will see that in many statistical applications, especially when you are working with data, this n is replaced by n minus 1. So this n is replaced by n minus 1 in order to define the standard deviation of x. But as far as linear algebra and we are concerned in this particular course, we will stick with this square root of n, not n minus 1. There are many statistical important reasons why this n minus 1 comes here and not n. Something like degrees of freedom in a chi-square distribution. So this thing is directly related to the degrees of freedom for a chi-square distribution. We will not worry about it right now, but this is just a reminder that you might see a different formula for standard deviation of x in a data. You will see n minus 1 there, not n. So there are interesting properties like chi-square distribution properties with n minus 1 degrees of freedom and unbiasedness of an estimator that sort of give you that n minus 1 term there, but we are okay with n. We are just fine, no problem about it. So an interesting observation is about average. Okay, so before going there, let's quickly look at something which is computational complexity. So we had been doing this discussion of computational complexity in second or third lecture, and then we have not talked about it. So let's see what is really happening. So if you want to find out inner product of two vectors x transpose y, so this inner product of x transpose y is basically summation xi yi I going from 1 to n, which means that you have to do n multiplications and n minus 1 additions, right? So this is what you want to do in order to compute x transpose y. So the total number of operations that you are required to do is 2n minus 1. So this 2n minus 1, I will just roughly consider this number of operations to be equal to 2n. 2n minus 1 and 2n does not really make much difference when n is a very large number. So how many number of operations, what is the computational complexity of evaluating norm of a vector x, 2 norm of a vector x? So what are you doing? You are taking square root of x transpose x. So x transpose x, how many operations are required? Roughly 2n operations are required. So this is 2n minus 1 to be precise. And then you want to take a square root. Okay, then take square root. So this square root operation is a really very difficult, interesting and challenging operation in floating point arithmetic. But we are not going deep into floating point arithmetic, and we'll just assume that taking a square root is equivalent to one operation. So this is one operation. So total 2n operations are required, 2n operations in order to compute 2 norm of any vector x. So this is so far so good. So now how many operations are required in averaging of x? Averaging of x. So averaging of x is basically 1 transpose x divided by n. So 1 transpose x requires 2n minus 1 operations. And you have one division by n. So 1 transpose x, basically if you see, if you are little bit clever in doing this, it does not require really 2n minus 1 operations, because you have a vector of 1s which is only constants, and you basically are doing only n additions. You are just adding up the vectors, so n, and division by n, one operation. So the total number of operations is basically n plus 1 operations. So if I want to do some approximation later, I will not really worry about n plus 1 operations. I'll just say roughly equal to n operations. Okay, so that's what I'll use. So here also x transpose x, I will say roughly n operations. N minus 1 is roughly n operations. For n very large, so n is 100, so 200 minus 1, 199, and 200 doesn't make much difference to me. So that's what really I'm saying. So if you want to compute RMS value of x, what are the number of operations? So RMS value of x, what is the formula? RMS value of x is summation xi square divided by n square root, right? So square root of x transpose x divided by root n. So that's what you want to do. So x transpose x will require roughly 2n operations. Then you have to divide by, so 1 division, 1 square root. So that's how much you require for RMS value of x. And if I want to find out standard deviation of x, how many number of operations will be required? So standard deviation of x requires x minus 1 transpose x, 1 transpose x divided by n into 1, it's 2 norm divided by square root of n. That's what you want. So 1 transpose x divided by n, average. So how many operations are required in average? N operations roughly, right? Then you have that average multiplied. So you have that average vector. You have to subtract x minus average vector. So that subtraction is n operation. Then you get this vector inside whose two norm is to be calculated. So this vector has n components. So for those n components, if you want to compute the norm, then norm is 2n operations, right? Then 1 square root and 1 division by root n. So these are like n plus 2 and 4n plus 2. These are the number of operations that will be required in order to compute the standard deviation of x. So these are certain computational complexities. So as n increases, you can see how many number of computations are required. and so on and so forth. So that is something that you have to look out and you have to be aware of. So before going further, we just let us note an interesting relationship between average, RMS value and standard deviation. Okay, so I just abbreviated standard deviation by SD. And what is the formula? The formula is for any x in Rn, RMS value of x, the square, is actually equal to average of x, the square, plus standard deviation of x, the square. Okay, so how do we prove this particular formula? I'll write down the proof very quickly, but the reason why I want to write down is to make sure that how we perform those operations involving inner products. Okay, so I'll consider this standard deviation of x whole square. We start with there. How is it defined? It is defined as 1 upon n norm of x minus 1 transpose x divided by n into 1, this 2 norm whole square. That's how we define. So this is 1 by n, and you have a vector x minus y, it's 2 norm square. So basically it is x minus y inner product x minus y. So x minus y transpose x minus y, and I'll expand that x minus y transpose x minus y. So I have this 1 by n, and this 1 by n is accompanied by this first term x transpose x. Then I have this 2 times x transpose and inner product here. So I have this 1 transpose x divided by n into 1. So that's what I have. And then I have inner product of this vector with itself, which is nothing but 1 transpose x divided by n 1. And I have transpose of this term into 1 transpose x divided by n and 1, right? So you have to understand that this term is a scalar term. So this term is a scalar term. So this is a scalar. You have to please always remember that. So this term similarly is a scalar term. So this scalar term I can pull out, and then this is actually inner product of x and 1. So this is something that you have to understand. So this is a constant term. This is a scalar term. So I can combine this scalar with 2, because it's x transpose scalar vector 1. So that scalar can come out, and I have 2 into this scalar highlighted in red into x transpose times 1. And same thing, same story with this particular scalar. So this scalar is, so I am using the property that inner product is associative. So it doesn't matter in what order I do inner product. So these scalars which are accompanying the vectors, I can pull out into the bracket. So this will be like average square for me, and then I have 1 transpose 1. So 1 transpose 1 basically is 1 into 1, right? So 1 transpose 1 is vector of 1 times vector of 1. So 1 into 1 1 plus 1 n times. So 1 transpose 1 is basically n. So this is what n times average square. That's what this term is really going to be. Let us try to understand and simplify these steps. So you have this as 1 by n, and you have x transpose into x minus this 1 transpose into x by n. So this term, you will agree with me, is basically 1 transpose x whole square. And you have a term here which is n into 1 transpose x divided by n whole square. So this n is coming out because of 1 transpose 1. So that is what you have to remember. This is 1 transpose 1. That's how you get this particular term. And you have this 1 transpose x, and then you have x transpose 1. So 1 transpose x divided by n I have come out, and then you have 2 times x transpose 1, but x transpose 1 is same as 1 transpose x. So here I am using x transpose 1 is same as 1 transpose x. That's the reason I have used, and then that's why I get a square term there. So if you see, I have all the terms that I really need. So I have 1 transpose x whole square divided by n basically. So this term, the way I adjust, so this 1 by n gets multiplied to this minus 2 by n. So if I simplify, I hope you will agree with me that I'll get x transpose x divided by n minus 1 transpose x, that's this term, divided by n whole square. So that's what I'll get. And this is nothing but x transpose x divided by n is RMS, this is RMS square, RMS x square minus average of x square. So that's what I am getting. So rearranging the terms, I get this particular formula, the star formula. And apart from the physical interpretation that this formula might offer, there is an added interest in knowing this particular formula, because there are two things that I will like you to explore. The two things that I will like you to explore, they are as follows. So the first thing is, can you physically interpret? Okay, so can you interpret this formula for a data vector x? Okay, so this is something that I want you to think about. And the second thing that I want you to think about, so work out, is actually computational complexity of this particular formula. So what is computational complexity? Computational complexity for computing standard deviation of x. So it looks like standard deviation of x, the way we defined it, and this is another way of computing this particular formula. So RMS of x square, what is the evaluation of RMS? Evaluation of RMS, we just wrote somewhere, right? So evaluation of RMS is 2n operations, and you just check how many number of operations looking at the whole thing this standard deviation requires, and this formula that we wrote down, how many number of operations this formula requires, and is one way computationally better than other. Okay, that's something that you can explore. That's what I want you to check. Okay, so this is about standard deviation. And we wrote down Chebyshev inequality yesterday. We wrote down Chebyshev inequality. Let us write down this Chebyshev inequality for the vector x hat. Right. So what was the Chebyshev inequality in general? So the Chebyshev inequality said that you let x to be a vector in Rn, and let there be k entries. Let there be at least k entries in x such that mod of xi is greater than a for some positive a. So this is what was the given. And then what does the Chebyshev inequality said? Chebyshev inequality said that this ratio k by n was actually Rmx of a divided by a whole square. Right. So this was Chebyshev inequality that we actually proved yesterday, and we can actually apply this Chebyshev inequality on x hat, which is nothing but x minus average of x1, that vector. So what are we really saying? So for some a greater than 0, for some a which is greater than 0, we are saying that there are k entries in x hat. And what is the property of those k entries in x hat? The property is that mod of xi minus average x is greater than a. So this entry xi deviates away from average value of x by an amount of a, by an amount at least of a. That's what we are saying. And how many entries are there? How many such entries? K such entries are there. Then Chebyshev inequality implies that K by N is less than or equal to RMS value of X hat now, but RMS value of X hat is nothing but standard deviation of X. So, standard deviation of X divided by A whole square. So this inequality is really very interesting when you have this positive number A that is greater than standard deviation of X. So, in particular, if I take A to be equal to 3 times standard deviation of X. Okay, so this 3 times standard deviation of X is something really very interesting. So, if I take this particular thing, then what am I saying is that Xi minus average of X is greater than 3 times standard deviation in the vector X. So, this particular entry Xi in the vector X is deviating away from the standard from the typical value of X, the average of X, by at least 3 standard deviation distance. So, that is what I am saying. So, this this Chebyshev inequality is actually telling us how many such entries in a vector can be there. So, if I take A to be standard deviation of A, then K by N is going to be less than or equal to 1 by 3 square, which is equal to 1 by 9. So, what are we saying? We are saying that there can be at most 1/9 of the entries in the total vector. So, 1/9 is roughly 11 to 12%, right? 11 to 12%, I am not very sure. So, roughly 11% of the entries at max can deviate away from the typical value, from the average, by a distance of 3 standard deviation. The other way of looking at this Chebyshev inequality result is something very interesting. What does it say? The entries in the vector X within the 3 standard deviation from the average value of X is at least 89%. So, at least 89% of the entries have to lie within this interval. So, what is that interval? The interval is average of X minus 3 times standard deviation of X less than or equal to Xi less than or equal to average of X plus 3 times standard deviation of X. Okay. So, this Xi, how many such Xi? How many such Xi? At least 1 minus 1 by 9, that is 8 by 9 of the total entries, which is nothing but roughly 89%. So, roughly 89% of the entries, at least 89% of the entries have to lie within this interval. So, this is something that is a very good result, right? But this result is useful only when you have this A to be greater than standard deviation of A. If A is less than standard deviation of A, then this result really is of no use to us. And I bet you have seen this something. So, right, this minus 3 sigma to plus 3 sigma. Oh, okay. By the way, I hope you understand how I got that inequality from this inequality, right? So, this inequality is there and this inequality is there. So, these inequalities, how do I get? I hope you understand. Mod X less than A is same as saying minus A less than X less than mod A. I am using that to say this. And this something is really very good thing that you might have observed previously. You might have heard something like 6 sigma, right? So, in statistical analysis, standard deviation is always called as 6 sigma, and you might have heard 6 sigma analysis. So, what is that 6 sigma analysis? 6 sigma analysis says that all the entries within that 6 sigma band. What is the 6 sigma band? This is the 6 sigma band that you have obtained, right? The length of this interval, that is 6 sigma. So, that 6 sigma length of the interval should contain so many number of entries. So, we are saying here by Chebyshev inequality, at least 89% of the entries should be contained within that 6 sigma band. That is what we are saying here. But there are certain statistical distributions which are much more interesting, in the sense that there is a distribution which is called as normal distribution, which says that almost all entries should lie within this 6 sigma band, 99.99% of the entries. Here we are saying at least 89% of the entries should lie within this 6 sigma limit. So at least means that that's the lower bound. It has to satisfy 89%, but it can be more than 89%. So that's something that you should remember. So the whole statistical Chebyshev inequality and the Six Sigma analysis that you see, its root lies in these inequalities that you are obtaining because of inner products, norms and definitions of RMS and standard deviation. Okay, so that's what we are really looking at. And before I go further, this is one final operation that I want to talk about: standardization of X. Okay, so this is something that you will almost always do when you work with data. So what do? You construct a vector x hat, which is nothing but x minus average of x into 1. So you have subtracted the mean of this vector, and then what do? You divide this vector by standard deviation of x. So when you do that, all the entries of this x hat are between they are around 0. Okay, the values are around 0. The positive value means the given value is the given value of this vector x tilde. Maybe I'll call x tilde because I already have used x hat for the numerator. So this x tilde has n components. So this is a vector in Rn, and this vector is basically x1 tilde, x2 tilde, so on so forth up to xn tilde. And the vector and the entry xi tilde is generally called as score. So this vector many a times is called as score vector. And what is this xi tilde telling you? Xi tilde is telling you with a positive or negative sign, either it is less than the typical value or the greater than typical value, and by how much, because you are dividing by the standard deviation, by how much. So if certain xi tilde is say 1.3 and some xj tilde is 0.2, then you can say that the value xj is closer to the mean than value xi in the original vector x, and these are actually the proportions. So how close or how far away, that is what is measured. And this value, if it is negative, then you know that it's less than the mean value, less than the typical value, whereas this value xj is greater than the mean value. That is what you have to understand. So you will always many a times you will perform this standardization operation. So this standardization operation is basically this operation: x minus average x into one vector divided by standard deviation of x. So that's that vector x tilde, the score vector, will have this information about the original vector. Now once we understand this, okay, so one exercise for you to look at is computational complexity. Okay, so you have to find out what is the computational complexity involved in computation of x tilde. How many number of operations you are required to do. So once we have done this standard deviation, Chebyshev inequality, interpretation of those things, we move on to the next concept that we can define using inner products, and that is of angle between the vectors. But before that, let us recall Cauchy-Schwarz inequality that we proved in the previous class. So Cauchy-Schwarz inequality. So what did Cauchy-Schwarz inequality say? For any vectors x and y belonging to Rn, x transpose y is in absolute value is always less than product of 2 norm of x and 2 norm of y, right? This is what Cauchy-Schwarz inequality told us. I can rewrite this Cauchy-Schwarz inequality in this particular way, which says that this is less than or equal to 1, and this is same as saying minus 1 less than or equal to x transpose y divided by 2 norm of x, 2 norm of y less than or equal to 1. So what we know is that this particular entity x transpose y divided by norm of x times norm of y always lie between minus 1 to 1. And we will use this particular entity to define the angle between the two vectors x and y. So the angle between the vectors x and y in Rn is defined as theta is equal to arc cos of x transpose y divided by norm x norm y. And obviously we are dividing by norm x and norm y, so we are assuming that this is not equal to 0. This is not equal to 0. So we will always talk of angles between two non-zero vectors, okay, and the angle between the two non-zero vectors is given by this. And what is this arc cos? Arc cos is an interesting function. What is the arc cos? So I did not write cos inverse, I wrote arc cos. So this arc cos is standard. So I hope you know the graph of this is pi by 2 and this is pi. So how does the cos function look like? It looks like this, right? So between 0 to pi, this cos function is a 1 to 1 onto function, invertible function between 0 to pi, and takes values between 1 and minus 1. In fact, takes every value between 1 and minus 1. So on to range minus 1 and 1. So you can talk of inverse of this function cos between the interval minus 1 to 1, and that's what we are precisely doing. We are looking at the interval minus 1 and 1, and the values here lie between minus 1 and 1. So what is the value of theta? You will get a unique value of theta between 0 to 2 pi, and for that unique value of theta you will see cos of that value of theta is basically this number x transpose y divided by norm of xy. So that's how you define this angle theta between the two vectors. So this implies that cos theta is basically equal to x transpose y divided by 2 norm of x into 2 norm of y, which is same as saying x transpose y is equal to cos norm x norm y cos theta. So I can write this down. So in particular, if x and y are such that they are unit norm vectors, so norm of x is 1, norm of y is 1, then x transpose y is actually cos theta, and this is how we have studied, this is how we defined angle between the vectors x and y in coordinate geometry in school. So the concept of vectors, angle between the vectors actually matches with this particular formula. And a few things that we need to observe is the following. So observation 1 is that if x transpose y is equal to 0, then theta is equal to pi by 2. We call the vectors orthogonal vectors. Okay, orthogonal are perpendicular vectors. So this is something that you have to remember. You already know, most probably, no big deal. If theta is equal to 0, then cos theta is equal to 1, and that means that x transpose y is basically 2 norm of x times 2 norm of y. And what does that mean? Theta is equal to 0, that means that the vectors are actually the same vectors, right, in the same direction. So one is scalar multiple of the other, the scalar being positive. And the second thing that you can look at is if theta is equal to pi, then cos theta will be equal to minus 1, which will imply that x transpose y is actually negative of x norm x into norm y, and that means that the vectors are on the same line but in the opposite direction, and this x transpose y basically is product of norms with a negative sign. That's what we will have. And the fourth thing is that if theta is less than pi by 2, 0, then we call acute angle between the vectors, and if then we call obtuse angle. So this is some terminology, and this is a very important consequence. We will use the first consequence often to use this orthogonal vectors. So probably in a lecture, maybe tomorrow, the next lecture, or sixth or seventh lecture, will extensively use these orthogonal vectors in the vector space Rn, and we will talk about interesting properties of those orthogonal vectors, and why these things are really special for the applications that we are considering. So we will talk about that. And the thing that you have to remember is the following. So in R2, for example, what is going to happen really? So you have to sort of understand this concept really very well. So in R2, okay, forgive my drawing and assume that this is a circle. Okay, this is a unit circle, and this is the point x and this is the point y on the circle. Then the distance of this point x from y on the circle is something that I want to understand. So because I am considering the unit circle, I can consider the circular distance. I can consider the circular distance to be angle between the vectors x and y, right? I can consider this distance to be equal to angle between the vectors x and y. So that angular distance will be basically this, whereas if you look at the Euclidean distance between these two vectors, then that Euclidean distance will be actually this. Okay, so maybe I can use a different color to show you that this is the Euclidean distance. So this is x minus y, Euclidean distance, and this circular distance or angular distance is basically this along the circumference, right? So this is this distance. So I can define similarity between the vectors either by using the angular distance or circular distance or the Euclidean norm distance. So for example, I can have two vectors in R2. Oh, by the way, you can take this concept forward in R3. So in R3, you will be looking at a sphere. So instead of unit circle, if you choose circle with radius r, then what happens? You have radius r here, and you multiply this by radius r. That's the circular distance on circle with radius r. And you can totally take this concept to R3, where you will be looking at sphere with radius r, and you want to find the spherical distance. So distance on the sphere between the 2 points on the sphere x and y. So those 2 points on the x and y, so you can really understand this in a nicer way. So what is the nicer way? Why Euclidean distance may not be of use, but angular distance or the spherical distance be of use in application is that Earth is roughly spherical, right? So there are 2 points on Earth, so 2 cities, and you want to find out the distance between 2 cities. The Euclidean distance will be the chord, right? You cannot travel along the chord, you have to travel on the surface of the sphere. So you need to know the spherical distance between the 2 points x and y. Now consider this, if those 2 points x and y are very close to each other, then what will happen? The angular distance, so the length of arc will be roughly same as length of the chord, right? So this is basically length of arc xy that I am really looking at, and the Euclidean distance is length of chord between the points x and y I am looking at. If the angle theta is very small, then what happens? The length of chord is roughly same as length of arc, and this distance does not make much difference to me. But if I have this particular angle theta very large, then these two differences are different, and they will make a significant change in the understanding of similarity between the 2 points. That is something that has to be understood properly at this point, because from application point of view, this is going to play a really very crucial role. The next thing that you have to understand is the following. So suppose I have this vector here and I have a vector, the angle between these two vectors is really very small. Okay, so the angle between these two vectors is theta. The angle is really very small. Then what I have to say is the following. If the angle between them is small, I look at different circle. Okay, different circles. So on these circles with different radii, what is happening? As you increase the radius of the circle, the angle between the two vectors is still the same. This circular distance is something that you will look at, and the spherical distance is something that you will look at. Okay, so these are the two different distances that you look at. But one more thing that you have to understand, and that thing will be very important in understanding singular value decomposition, surprisingly, is that these two vectors, the point on the vectors, the distance between them is increasing as you go further, Euclidean distance, but the angle between the vectors is still the same. It's still a very small angle. Okay, so this concept I will use once again when I talk of something which is called as linear independence of vectors, and which vectors will call almost linearly dependent, and based on that almost linear dependence, we will relate that concept with singular value decomposition. So this is going to be a very interesting thing to look at. So please remember that this is something that is going to happen, and we will make use of the concept of angle little later. So this is what I wanted to talk about: norms, distances, similarities. So instead of looking at Euclidean distance between the vectors, feature vectors, you can employ angular distance between the feature vectors using the cos theta of the angle between the vectors, and you may get different results. So which similarity to use, or which distance to use in order to get the similarity that you are looking for, is again a subjective choice, and you have to make that subjective choice based on the application that you are working with. So linear algebra is there, but which tool in linear algebra you want to use, which distance in linear algebra you want to use, that is something that you have to decide based on your experience and based on the application that you are working with. So in summary, what did we do? So in summary, we defined from a vector x in Rn, a vector x hat which is obtained from x by subtracting the mean of the vector x. So this is demeaning, and then we had this x tilde where so we defined a standard deviation of the vector x as RMS value of x hat, and we also computed this vector x tilde, which is nothing but x hat divided by standard deviation of x, right? So that's something that we computed. So this is like standardization procedure. So this is like standardization process, standardization. Okay, then we talked about Chebyshev inequality for x hat, and that Chebyshev inequality for x hat actually gave us some interesting insights into the data, the entries in x, entries in vector x, if they are interpreted in data terms. We also found out relationship between root mean square of x, standard deviation of x, and average of x. So we derived that particular formula for those three things. We related those three things together. We talked of computational complexity, and we sort of evaluated the computational complexity for each of these operations that we have looked for in today's class. And then we defined one of the most useful things, angle from inner product. So we used Cauchy-Schwarz inequality to use that, and cosine of the angle between them. So we used this concept of angle, and with respect to that we defined another similarity measure or another distance, right? So distance based on angles. So that's what we looked at in today's class. Thank you very much.